Hello everyone. Today our lecture is circular motion. Before going further in circular motion, let's distinguish between circular motion and rotational motion. In rotational motion, an object is moving around its center, like an earth is moving around its center to produce day and night. So an object, so this center here and here, an object is moving around its center. This is called rotational motion. In circular motion, the situation is quite different. An object is moving around another center, like a moon is moving around the earth. If this is the earth here and there's the moon here, so it's moving around the earth in a circular path. This is called circular motion. Another example of circular motion is a simple pendulum. It's like this one here. An object is tied with a rope like this one here, and this here it's moving like in this one here. This is called circular motion. Two types of circular motion we would like to identify here. The first one is uniform circular motion. If an object of mass m is moving with constant velocity in a circular path, this is called uniform circular motion. In this case, we will have two types of accelerations. A tangent, in this case here, which equal to 0 because the object is moving with constant velocity. And there's another acceleration in this case here. It's a radial acceleration. It's called AR. And this radial acceleration, the magnitude for this radial acceleration, it's equal to v squared over r. In such a way, r here is the radius of the circular path, and v here is the velocity. Since we have two types of acceleration, a tangent and a radial, we will have two types of forces. Tangent force, so the net force, sum of all forces tangent here, it's equal to m a tangent. In this case here, sum of all forces in the tangent direction equal to 0. But for the radial direction, sum of all forces in the radial direction, it's equal to m a radial, which equal to, in this case, mv squared over r. Now let's identify the period. The period is the time required for an object to complete one revolution around the circle. Let's have this model. In this model, as we can see here, 4 different masses connected with strings, and the strings have the same length. As we can see here, the object's mass doesn't make any difference in the period diagram here. Now another different situation here, the 4 cases here have the same mass, but the string length is different for each case. And based on this, as we can see here, the period actually is different, and it does depend on the string length. So each string length has its own period. Based on the previous models, the period, which identified as capital T here, is equal to the length of the path or the circumference of the circular path, 2 pi r divided by v, and it measured in seconds. Let's have an example. In this example, an object of mass m is suspended from a string of length L. The object rotates with constant speed v in a horizontal circle of radius r. Find the speed of the object. Before going further in this example, let's have this model. In this model, as we can see here, an object here is rotate in horizontal circle like this one here, and it sweeps like a cone. This is, by the way, called conical pendulum. Now in this example here, this is theta, and this is the rope used to connect this object with length L, and the radius for this circular path, this one here, it's R. The question is, find the speed of the object. So if we start this one here, it rotates in a horizontal circular path. As we can see here, two types of forces we should have here: the tension, which is directed this way here, and the weight, it's directed downward to the center of the earth. Now to work with this one here, let's analyze the tension. So if this is theta here, so this will be theta here. So the tension was in here, this is tension. Let's just make it more different here. This is tension, this one here, tension. This is tension, this one here. So the y component, the one with the angle, takes the cosine, and the one without the angle takes the sine. So we should have here t cosine theta and t sine theta. So this circular path here. Let's go back to the example. Let's regraph this situation here. This is the length L, and this is the object with mass M. Okay, and this is the circular path, as we mentioned before, this one here, and this is theta, and this is R. In this case here, let's identify the forces we have here. We have the weight is directed downward here, this is mg, and this is the tension, it's directed this way here. Now we need to analyze here the tension. So this is theta here, so we will have here t cosine theta, and we will have here t sine theta. Now to solve this, we need to find the speed. Now sum of all forces on x equal to mv square over r. Now sum of all forces, this is x here, it's t sine theta equal to mv square over, now r here, it's r small, like in this one here. Now sum of all, this is the first equation here. In the second equation, sum of all forces on y equal to 0, tension cosine theta minus mg equal 0. In this case here, tension equal to mg divided by cosine theta. If we plug this one here back in this equation here, plug this result here back in this equation here, we will see that mg tan theta equal to mv square over r, mass with mass, and v in this case equal to square root of r g tan theta. So the speed here equal to rg, the square root of rg tan theta. Now in terms of the length of the rope here, let's find r. So we have here right angle triangle. If this is r, the radius for the circular path, and this is the length of the rope, and this is theta. Now sine theta equal to r over L. So sine theta equal to r over L, and r in this case equal to L sine theta. You substitute this back in this equation here, you will find that the speed v equal to square root of L sine theta with g here tan theta, and this is the speed in case of the conical pendulum. Let's have another example. In this example, a 0.25 kilogram object is attached to the end of the string of length L equal to 2 meters and moves in horizontal circle. If the maximum speed at which the object can move before the string breaks is 15 meters per second, what is the maximum tension the string can withstand without breaking, assuming the string remains in horizontal circle during the motion? Let's have a quick sketch for this example here. So an object is moving in a circular path like this one here. It's actually horizontal circular path like in this one here. The radius for this circular path, this one here, equal to r. We need to find the maximum tension the string can withstand before breaking if the maximum speed is equal to 15 meters per second. Now let's identify the forces on this object. We have actually here two forces. One is the weight, it's directed downward here, and the tension going to the center of the circle. So there's a tension. Now sum of all forces equal to, now we have here circular motion, so we have a radial acceleration, so it's equal to mv square over r, and r in this case it's r small. Now all forces on this direction here is the tension, in this direction here is the tension, so tension equal to mv square over r. Now v equal to v max and equal to, in this case, 15 meters per second. You substitute this back in here, and the mass of this object is 0.25 kilogram, and r is the length of the rope, which equal to 2. You substitute these numbers in this equation here, you will get tension maximum actually equal to 28.1 Newton. Example, a 0.25 kilogram object attached to the end of a string of length 1 meter moves in a vertical circle. If the speed of the object at the lowest point on the circle is 4 meters per second, find the tension at this point. So we actually here have a circular path, this one here, and object is directed this way here, connected with a string. Before going with this example, let's have this model. Now, like the case mentioned in the example, we have here a swing, and this object is connected with a string, as in this case in here. It's just here. So this is the string. At the bottom here, we have this object is swinging back and forth, this case here. And as we can see here, the weight of the object is constant and the speed of the object is changing, and the tension actually is changing. Now let's have a quick calculations here. Sum of all forces on y equal to mv square over r. R here is actually the length of the string. Now sum of all forces, we have actually tension this way here, and mg, it's directed downward here. So tension minus mg equal to mv square over r. Now let's go back to the example. We have here in this example, weight is directed this way here, and tension is directed this way here. So sum of all forces on y equal to mv square over r, or in this case, tension minus mg, it's equal to mv square over r. In this case, the tension at the bottom here, right here, it's equal to mv square over r plus mg. Use the numbers given in the example, you will find that the tension it's equal to 6.45 Newton. Example, two equal mass rocks tied to strings are wired in horizontal circles. The radius of circle 2 is twice that of circle 1. If the period of motion is the same for both rocks, what is the tension in chord 2 compared to chord 1? Since the period is the same and tension actually is equal to mv square over r, then v2 it's actually equal to 2v1 and r2 equal to 2r1. So if you substitute this back in this one here, you will find T2 it's actually to 2T1. Another example, a 0.5 kilogram object rests inside a basket that is connected to a rod. The basket travels in a vertical circle with radius equal to 2 meters at constant speed 5 meters per second. What is the normal force acting on the object at the top and at the bottom of the circle? Also find the minimum speed at the top of the circle in such a way the object will not fall down. Actually, this example reminds us with another experiment. It's called loop to loop. In such a way, a pilot moves in a vertical circular path, like in this one here. The pilot head at the bottom of the circle is directed upward. However, at the top of the circular path here, the head of the pilot is directed downward in this one here. Back to our example here, we have also the same situation. In such a way, we have a basket, this one here, this basket here connected with the rope, and there's an object in here. In order for this object not to fall down, we have to find the minimum speed at the top. Also, we have to find the normal force acting on this object at the top and the normal force acting on this object at the bottom. This is the bottom here, this is the basket here, this is the other situation. Now, before solving this example, let's have this model. In this model, as we can see here, an object is moving in a circular path, like in this one here. At the bottom of the circular path, like this one here, we have actually two forces. One of them is the weight, now this one here, mg, and this one here is the normal force. And at the top of the circular path, right here, as we can see here, both the weight of the object, this one here, mg, and the normal directed downward to the center of the circular path. At the bottom of the circular path, this one here, the normal force, this one here, is greater than the weight. This mg, and this is the normal force. Let's go to the example and solve it. Now, to solve this example here, at the bottom of the vertical circular path here, let's find the forces acting on the object. Now we have two forces actually here. We have the weight of this object, which is directed downward here, and we have here the normal force exerted by the basket on the object. This is the normal force here. Now at the bottom here, sum of all forces on y equal to, this is circular path. This one here is circular path. So it's equal to, in this case, mv square over r. And now this one here, the force goes with the acceleration. Actually, we start with it. So normal minus mg equal to mv square over r, in this case here. So the normal force equal to mv square over r plus mg, which means the normal force is greater than mg. So to graph this one correctly, we have to graph it much or longer than what we did here. Now to solve this situation at the top of this is at the bottom. To solve the situation at the top of this vertical circular path, we actually have the weight, which again are going down here, and the normal force exerted by the basket on the object here, it's also directed downward here. Now again, in the loop-to-loop experiment, same thing here. The weight of the pilot is going down here, it's mg, and the normal force which exerted by the seat on the pilot is going here. This is the normal force. Sum of all forces at the top, sum of all forces on y equal to mv square over r, in this case here. Now both the normal force in this situation and in this situation as well, in both cases here, the normal plus mg equal to mv square over r, both of them directed to the center here with the acceleration. So in this case r here, in this case here, the normal force, it's equal to mv square over r minus mg, which means the normal force is less actually than the weight of the object. So to graph this one here, it has to be shorter than the mg. By substituting numbers here, you will find the normal force equal to 1.35 Newton. Now to solve the second part of the question, what is the minimum speed at the top of the circle in such a way the object will not falling down? In order to keep the object not falling down, the object has to be in contact with the path, just in contact with the basket. In this case here, the normal should be greater than 0, but as we solved before here, we just found that normal equal to mv square over r minus mg. In this case here, mv square over r minus mg has to be greater than 0. You solve this one here, mv square over r is greater than mg. It has to be greater than mg, or in this case here, v equal to square root of rg, and you substitute numbers here, you will find the speed is greater than 4.43 meter per second. The minimum value here has to be equal to 4.43 meter per second. This is the minimum value of the speed in order for the object not to fall down. Now let's discuss another example of vertical uniform circular motion. It's a Ferris wheel. So let's have here example. In this example, a Ferris wheel of radius r rotates in a vertical circle at constant speed v. This one v. Determine the apparent weight of the rider of mass at the bottom of the ride in terms of r, v, and m. And again, what is the apparent weight of the rider at the top of the ride in terms of the same parameters r, v, and m. Now, before solving this example here, let's have this model. In this model here, as we can see, actually we have two forces. In this case here, the weight for the child is going down here, it's mg. Now, we're not actually interested in the tension because this is connected with the cart itself, and we are interested in the child itself. So there's a normal force exerted by the cart on the child. It's directed this way here. It's the normal force. Now, the normal force in this case is greater than the weight. We will see that mathematically in a moment. So the normal is greater than the weight of the child. Now, if we go further in this Ferris wheel experiment, let's see here what's going to happen. Look here, we're not interested in the tension. We're actually interested in the normal force, still decreasing here at the top of the circular path here. As you can see here, the situation is a little bit different from loop-to-loop experiment. The example we just mentioned a few minutes ago, as the head of the child is going up, it's not going down. In this case, the normal force, in this case, it's not tension. Again, just a quick reminder here, the normal force exerted by the cart on the child is going up, in this case here. So the normal, as we can see here, the normal force is shorter than the weight of the object. So the normal, it's less than the mg. Now let's continue here. As we can see here, the normal force is changing, and it's the maximum value at the bottom and the minimum value, it's right here almost in this situation here. Back to our example here, we have a child or a rider inside a cart in the Ferris wheel, and this here, the situation here. And the rider head at the bottom will be this way here, and at the top, the rider head is again, it's up. It's not like loop to loop. In this situation here, at the bottom, let's solve it at the bottom. Sum of all forces on y equal to its circular motion. So there is a radial acceleration, so mv square over r. Now, at the bottom here, let's identify the forces acting on the rider. We have here the weight, and we have here the normal. Again, the normal is the force exerted by the cart on the rider. This is the normal. Now, if the cart is connected by a rope, this is actually called a tension, but we are not interested in calculating the tension in this example. So in this case here, the force with the acceleration, you start with it. So in this case, normal minus mg equal to mv square over r. In this case here, the normal actually it's equal to mv square over r plus mg. It's almost the same situation as before at the bottom for either case, in this case or in the loop-to-loop case. However, at the top here, we actually have two forces. The weight is directed downward in this one here, and we actually have the normal force in this case here. Now, the situation here is different. So sum of all forces on y equal to mv square over r, and in this case, the one or the force directed with the acceleration, you start with it. So mg minus normal equal to mv square over r, or normal equal to mg minus mv square over r, which means the normal force is less than the weight of the object at the top of the loop. Another example, a 1200 kilogram car goes around a horizontal track of radius 150 meters at a constant speed. So it's uniform circular motion of 25 meters per second. What is the force of static friction acting on a car? Now let's just imagine the situation here. We have a circular path, as we can see here, this one here, and this is the car here. A car moving in a circular path, actually two types of frictional forces applies here. The first one is the kinetic friction, which is the friction between the tires and the road that makes the car move forward. The other one that we are interested in, the static friction. In order to keep the car not moving in or out a circular path and keep the radius for the circular path exactly 150 meters, is the static friction, and that's what we are looking for. In order to solve this example here, now sum of all forces here equal to mv square over r, or in other words, the all forces that we have here is the static friction. So static friction here, actually it's equal to mv square over r. We do have the mass of the car, the speed of the car, and the radius of the circular path as well. You substitute these numbers back in this one here, you will get the static friction equal to 5,000 newtons. Another example we have here, a car moving on a flat circular track of radius 150 meters. If the coefficient of static friction between the tires and the road is equal to 0.6, find the maximum speed the car can have and still make the turn without slipping. Now, in this situation here, now if we draw here the circular path, and this is the car, again, we are interested in the static friction that makes the car complete the turn without any slipping. And we look for the maximum speed the car can engage in the circular path and complete the circular track here without slipping. Again, sum of all forces equal to mv square over r. In this case, again, we all agree that the forces here is only the static friction. It's equal to mv square over r. Since we all know that static friction is less or equal to mu s n, and we are looking for the maximum speed, in this case, fs here is actually equal to f maximum, or f maximum here it's equal to mv square over r. Actually, it's maximum here. Now, F max actually it's equal to mu s n equal to mv square max divided by r. Now, if we take the forces acting on the car, we have also the weight for the car, it's mg here, and the normal. And remember, this is the horizontal circular path. This is the normal. Now, sum of all forces on y equal to 0. Or we can say this, normal minus mg equal to 0. Or in other words, normal equal to mg. you substitute this back in here, mg mu s equal to m v square over r, mass with mass, and the maximum speed actually is equal to square root of r g mu s. We have the numbers. You substitute the radius, it's equal to 150, g equal to 10, and mu s equal to 0.6. So the Vmax here equal to 29.7 meter per second. A more interesting example is this one here. In this interesting example, there's a frictionless rod of radius r is banked. Rather than going in a circular horizontal path, the rod is tilted a little bit with some angle theta here, like in the race tracks. So the car can round the rod at a constant speed v without skidding. Now remember, there is no friction in this rod here, it's a frictionless one. Calculate the banking angle in terms of r and v. So we are looking for this theta here. Now to solve this example here, now let's do the free body diagram. Now the weight is directed this way here, the mg, this one here, and this is the normal is directed here. In the previous lectures, we actually rotated the xy coordinates and make them match with the normal, and we analyzed the mg. The situation here is different. We will analyze the normal force, and if this is theta with some a little bit of geometry, this will be theta as well. Now after analyzing the normal, so the normal here cosine theta, and the normal here sine theta. The reason why we actually analyzing the normal, because the center for the circular path, it's like in this one here, not actually in this one here. Now without further to do here, let's just do the calculations. Sum of all forces here equal to mv square over r. F here is the n sine theta equal to mv square over r, and sum of all forces on y equal 0. Sum of all forces on y equal to 0, and in this case the normal cosine theta minus mg equal to 0, or we can say that the normal cosine theta it's actually equal to mg. By dividing this equation here on this equation here, we will get tan theta equal to v square over rg, or we can say that theta it's actually equal to tan inverse v square over rg. All what we discussed so far is the uniform circular motion, and again, uniform circular motion, the speed of the particle is constant, which means there is no tangent acceleration, which means the acceleration, the radial acceleration actually is perpendicular to the speed. But for non-uniform circular motion, the speed is not constant, which means there is a tangent acceleration, and in this case the resultant acceleration is not perpendicular to the speed. Now let's see this one here. We have a circular path. If the object here is moving with non-uniform circular motion, it's actually having tangent acceleration, and it actually have the radial acceleration. and the resultant one, which is somewhere here, is A. Now A in this case is calculated, A tangent here is actually calculated by the first derivative of V with respect to time. Now in this case here, AR is equal to V square over R. Now let's have an example. A small sphere of mass m is attached to the end of a cord of length r and set into motion in a vertical circle about a fixed point. Determine the tension in the cord at any instant when the speed in the cord makes an angle theta with the vertical. So the situation, it's like here. So if this is theta here, this is theta. And the forces we have tension right here, and weight, it's like in here. If this is theta, so this will be theta as well. Now, after analyzing the weight, we'll get here mg cosine theta, that this way here, and mg sine theta. Now, sum of all forces, in this case here, tangent, actually, it's equal to a tangent. In this case, mg, this one here, mg sine theta equal to a tangent equal to g sine theta. Now to find the tension in the cord, let's analyze this one here. Sum of all forces radial equal to T minus mg cosine theta, which equal to mv square over r. Therefore, tension equal to m times v square over r plus g cosine theta. That's it. Thank you for watching.